Okay, so there is another class of general class of problems that also admits limit theorems, and this is the class of problems that have to do with maxima and minima of many random variables. So again, we consider a sequence of IID random variables with a certain distribution P of x, and I'm going to also define the cumulative distribution as the probability that the random variable xi is less than x. Okay. Now, the problem we want to study is we want to characterize the random variable Zn, which is the maximum of the first n of these random variables, or we want to characterize the minimum of the first n random variables. Okay. And we want to do characterize these random variables when n is very, very large. And by this, it means that we want to understand how big they are and what is their distribution when n goes to infinity. Okay, so there are a lot of problems that that are of this form. Saying, for example, in engineering, there is a lot of problems where essentially you want to design objects in such a way that they are robust, and if they are subject to perturbation, then you want to make sure that they can resist a large number of perturbations. So you also, if you imagine that you design a bridge, for example, and then at every year you have possibility of floods, then if xi is the level of the water, is the maximum level of the water in every year, then you want to make sure that your bridge is higher than the maximal level of the water that the water can reach in many years, where this number of years may be larger than the engineer lifetime. Okay, or say if you are at a bus stop and you are waiting for a bus, and there are many buses that can arrive, then you are interested in, and xi is the time you have to wait for each of these buses. Then essentially you are interested in how much time you have to wait for the first bus, which is the minimum of the time of each of the buses. Okay, and also records are a problem of this type. A record, say, is an event where a random variable x is larger than all the previous random variable. So in general, there is a field which is called extreme value theory, which deals with this problem. What I want to do now is to give you essentially a crash course about these problems, concentrating on problems where random variables are just IID. Okay. So again, we want to cast the problem in the following question, and it is to find sequences AN and BN, which are real sequences such that if I write Zn as an plus Bn times lambda, then lambda n is a random variable with a non-degenerate distribution. Okay, so I want that the probability, the cumulative distribution of lambda n converges as n goes to infinity to a cumulative distribution that we call it h of x, which is non-degenerate. Okay, so this is the problem you see. It's a problem which is very similar to the one that we have discussed for sums. So I want to find these two sequences such that I can separate asymptotically the dependence from n and from omega, in the sense that when n is very large, the probability distribution of this random variable asymptotically is given by this non-degenerate distribution. Okay, and then I can understand how big is the maximum, and what are the fluctuations? What are the fluctuations that I can expect? Okay, of course, the problem of the minimum is exactly the same as the problem of the maximum, because if I take minus the maximum, then it becomes a problem of if I take variables. If I change the sign in the variable xi, then this problem becomes this problem. Okay, so I will only discuss the maximum, the problem of the maximum, and the minimum can be addressed very easily. Okay, so what is the main idea? So the main idea is the following. So of course, if you want to compute this probability that lambda n is less than x, then you want the probability that Zn is less than an plus Bn times lambda. Okay, Ex, sorry. Okay, because the relation between Zn and lambda is this. And so if the maximum is less than this, then it means that all the random variables must be less than, so this is equal to the probability that the xi are less than an plus bn x for all I. Okay? But now these events, these random variables are independent, so these events are independent. So this is the probability that xi is less than an plus bn times x for all random variable I, but they are also independent distributed. So this is exactly this probability raised to the power n. Okay. And I can rewrite this as 1 minus the integral from an plus bn x to infinity dx prime of p of x prime raised to the power n. Now, if I want a finite limit, if I want to find an and bn such that there is a finite limit here, then it must be that this object must be of order 1 over n. Okay? So the way to solve this problem is to say that if the limit, if I can find an and bn such that the limit as n goes to infinity of n times this integral is finite, and it's a finite function, okay, then this will be asymptotically equal to, so this object will be asymptotically equal to C of x divided by n, and the limit here will give me e to the minus C of x, okay. So, and which essentially should be my cumulative distribution of the random variable lambda when n goes to infinity. Okay. So the bottom line of this is that essentially the condition to find an and bn should be that this limit should be finite. So I should compute this function c of x, find an and bn such that this function is finite, and then I take it I take e to the minus c of x, and I get the cumulative distribution. Okay. So this is essentially the main idea. So now, if we want to discuss how this idea works, then we have to specialize to particular cases. So you see that because I want this probability here to be of order 1 over n, then I have to concentrate on the tail of the probability distribution. So depending on the behavior of the PDF in the tail, I will have different limits. Okay. So the first case, is when the probability distribution goes as a power law, say a times x to the minus gamma minus 1, when x goes to infinity. Okay. Then in this case I can take this object an plus en x, and I can estimate it because essentially here I have a times n times the x to the minus gamma minus 1, and the integral of this gives me 1 over gamma times an plus bn and x to the minus gamma. Now, if I want to make this finite, you see that I can take an equal to 0, so that this goes away, and then bn will be, I can take bn, which is a n over gamma to the 1 over gamma. Okay? So because if I do this, if I make this choice, then this bn to the minus gamma will be just this to the minus 1, so they will cancel, and I just get x to the minus gamma. Okay? So then this is my function c of x, and so you see that in this case the sequence are equal to this. So the size of the maximum will be given by n to the 1 over gamma, and the distribution cumulative distribution is e to the minus x to the minus gamma, which means that the density, the PDF, which is the derivative of this, is gamma x to the minus gamma minus 1 e to the minus x to the minus gamma. So you notice here that for x going to infinity, this limit distribution has the same form, has the same asymptotic behavior as the original distribution. So the limit of the maximum preserves the behavior of the random variables in the table. And again, you can see that this limit is universal in the sense that it does not depend on all the details of these random variables. It only depends on the behavior of the PDF for x going to infinity. Okay, so now it's instructive to see what to compare the behavior of the sum and the maximum for different values of gamma. So I remark that here, say gamma is positive, so we know that if gamma is larger than 2, so if gamma is larger than 2, then the maximum is of the order n to the 1 over gamma. But if gamma is larger than 2, then we are in the regime of the central limit theorem. So the sum of n random variables will be of order n times, so the sum of n random variables will be of order n, and the fluctuations in the sum will be of order square root n. So you see that in this regime, when gamma is larger than 2, then the maximum is much smaller than n, and it is also but it is also much larger than but it's also smaller than so in this regime Zn is much less than the fluctuations in the sum, and is much less than the sum itself. Okay? So in this regime, essentially the maximum does not contribute nor to the sum nor to the fluctuations of the sum. Now if we are in the regime gamma between 2 and 1, then again the maximum is of order n to the 1 over gamma. The sum is of the order n, and the fluctuations in the sum instead, which is the Bn for the sum, is of order n to the 1 over alpha. So now Zn is of the same order of the fluctuations of the sum, which is much less than the whole sum. Okay? Whereas if we are in the regime gamma less than 1, then again the maximum is of order 1 over gamma. But now the sum itself is of order n to the 1 over gamma. Okay? So in this regime you have that Zn is of the order of the fluctuation in Zn, which is of the order of the whole sum. Okay? So this tells you that, as we discussed, when the law of large number does not hold, then the sum is dominated by by the maximum. When instead you are in these other two regimes, then in this regime the sum only dominates the fluctuations in the sum, whereas in this one it is negligible both with respect to the fluctuations and with respect to the sum itself. Okay. Okay, so now let us go to the second case. Second case is a case where instead we have a distribution that has this shape as support on up to a certain point, and then this is the p of x, it's function of x, and there is a omega such that so all random variables are less than this omega. So, and at this omega you have a singular behavior of the form omega minus x to the gamma minus 1 for x less than omega, okay? And okay, so now if we look, we can look at this integral here, and n times an plus bn times x. The integral now will finish at omega. This integral will be of the order of a times omega minus x to the gamma minus 1. So now it is clear that this so if I do this integral, if I change variables here, I get x prime, I change it to a variable z which is omega minus x prime, and then you can easily do this integral, so you get a times n divided by gamma times omega minus an minus bn times x to the gamma. Okay. Now for this in this case you see that you can get a finite limit if you take an which is equal to omega, so that these two terms cancel. And then you can get bn, which is a n over gamma to the minus 1 over gamma. Okay? Because then this term bn to the gamma just is the inverse of this. And you get that essentially this is just minus x to the gamma. Okay, so then this is our function c of x. So if this is the function c of x, then the function h of x, and this is clearly only for x, which is negative. Okay, because x positive would correspond to this other side where. So h of x is equal to e to the minus x to the gamma. Okay, and the PDF, which is the derivative of this, is gamma times minus x to the gamma minus 1 e to the minus x to the gamma, again for x, which is negative. Okay? And so h of x is equal to 1 for x, which is larger than 0. Okay? And here the density is equal to 0. So you see that the density is exactly, again, the same singular behavior as the original distribution close to the maximum. Okay? And so in both cases, this singular behavior is conserved. Okay? Now, there is one particular case, which is gamma equal to 1, which is essentially the exponential. Okay? If gamma is equal to 1, then say h of x is equal to, say, minus x e to the x, okay, for x negative. So this means that this is for the maximum. So this tells you that the distribution of the minimum, so the probability that Wn, the minimum of n random variables, which now if you look at the minimum, you should look at functions which are inverted with respect to x. Okay, so there are support from some x onward, and gamma equal to 1 means that this function should have a distribution which is finite, a PDF which is finite at x equal to 0. Okay, so for any function of this form, the probability that the minimum is larger than x is essentially given by the exponential distribution with a Bn, which is essentially 1 over n. Okay. Yes. Yes, so the minimum of these random variables should be described by a distribution which is exponential. Okay? So this tells you that if you take the minimum of exponential random variables, you get an exponential random variable. And this is interesting, and it has an important application that I want to discuss because it is related to what is called QLS-PIT algorithm. So now imagine that you have a situation where you want to simulate a system where many different processes can occur in time, each of which is a Poisson process, so it can occur in every time interval with a probability that is proportional to the time interval for small time intervals. And but I want to simulate this process. So an example to give you an idea is, again, think about you are in the bus stop, and each of these processes is the arrival of one of the possible buses of the different type of buses. Okay, so you have these processes that occur in time at random times, and say there is a cross process, there is a square process, and there is the circle process, etc., etc. Okay, and now you see each process has a waiting time, so the probability that a process I occurs, that you have to wait a waiting time which is larger than t, is e to the minus ri times t. Okay, so the waiting time is exponentially distributed for each of these processes. But then now the thing is that the question you are interested in, you are at a certain point in time, and you want to simulate this process. Okay, you want to write a computer code by which you can generate a particular history of how this process occur in time. So this is relevant for when you do numerical simulations of many physical systems, where in each of these physical systems, so you have a large system, and at every point in time, many different processes can occur in a random way, and the waiting time for each of these processes is exponential. So one simple way of simulating this process is to say, well, let's fix a small time dt, and then the probability that process I occurs for small dt will be equal to Ri times dt, or if you want to be more precise, the probability that it occurs is 1 minus e to the minus Ri times dt. And then you draw a random number. If this random number is less than this, then you execute process I, and then you look at all processes. Imagine that you have n of these possible processes, and also imagine that n is very large. Then what you can do is just fix a dt, and then draw random numbers, see which of these processes occur, make them happen, advance t to t plus dt, and go on. Now this is very inefficient for several reasons. First of all, because when one of these processes occur, it may modify the probability that other processes occur, because what you're interested in is to simulate systems of interacting particles. And the interaction in the system means that essentially if one process occurs, maybe it modifies the likelihood that other processes occur. So what you want to do is to have a dt which has to be small enough such that at most one of these processes occur. But then this is very inefficient, because you are going to draw n random variables in order to execute just one process. Okay, one instruction. So, and also it means that you have to take a time dt, which is of order. You have to do order n operations to advance the time by 1 over n. Okay, it's very, very inefficient. Okay, So the other way of thinking about this is, okay, so I can ask directly how much time should I wait for the next process, okay? So what is the minimum time that I have to wait for the next process? And so the minimum time that I have to wait is the minimum over all processes of the time that I have to wait for process I, for each of the processes, okay? And so then I can apply the extreme value theory, and essentially the probability that what I have to wait is larger than some t will be equal to the probability that no process occurs up to time t. And if these have an exponential distribution, then this is just e to the minus some, well, it's just a product because they are independent of e to the minus ri times t. Okay, so this is the probability that process I does not occur up to time t, and because they are independent, then this is just given by this. Okay, so you see that the probability distribution of the minimum time is just e to the minus sum I from 1 to n of ri times t. So you can directly know, you know that what is the probability distribution of the minimum time. So you can directly draw the delta t mean by just drawing an exponential random variable with this distribution, okay? In addition, you can also compute what is the probability that the next process, let's say I star, that will occur is exactly the process I. So this is exactly the integral from 0 to infinity of the ti of the probability that process I will occur between ti and ti plus dti, which is this, times the probability that all the other processes will occur later. Okay, so this means you have to make the product over all the other processes of the probability that they will occur later than ti. Okay, and the probability is just e to the minus rj times ti. Okay, so you see that this is I can put these two things together and I can perform this integral, and this gives me just ri divided by the sum over all j of rj. Okay, so you see, so in order to do this process now, what I can do is I can draw at random which is the process that will occur next from this probability distribution, and then I can draw from an exponential distribution how much time should I wait for the next process, and I can advance time exactly to the time where the next process will occur, and I can execute this process, and this is much more efficient than just fixing a finite time dt, because you just draw two random variables for executing one event. Okay, so this way of doing numerical simulations is essentially called the QLS-PIT algorithm. Okay, so let's go back to our problem and discuss the final case, the third case, which is the case where the distribution is extends to infinity, well, the distribution extends to infinity, but it goes to zero faster than any power. Okay, so P of x goes to zero as x goes to infinity faster than any power of x. So this also means that if you take the expected value of x to the q conditional on x being positive, then this should be finite for all positive q. Okay? Okay, very good. So in this case, it is not easy to derive directly the form of an and bn. So I will just give you the results and derive them for a particular case. So in this case, an is fixed such that the probability that the random variable is larger than an is equal to 1 over n. So this means that the probability from an, the integral from an to infinity dx of p of x is equal to 1 over n. And then bn is given by the expected value of x minus an conditional on x being larger than an. So essentially this is a situation where this is your probability distribution, E of x. Then you fix an such that this integral here is of order exactly equal to 1 over n, and that the expected value, if you take at random one value of x which is larger than an, then bn is given by the expected value of this distance, okay, from a random point and an. Okay, and well, this you can also write it as the integral from an infinity in the x of x minus an times p of x divided by this integral an infinity dx p of x. Now this is clearly 1 over n, so this is n times, and this integral you can also write as the integral from an to infinity in the y, integral from y to infinity dx of p of x. Okay, so you can write it in different ways. Okay, and the limit distribution. So in this case, the function c of x that you find is the exponential, which means that the cumulative distribution is a double exponential, or if you want the PDF is e to the minus x minus e to the minus x. Okay, so if you look at what is this distribution, so this distribution, h of x, is a distribution that goes to 0 with an exponential. Here it goes as e to the minus x. This should be h of x. And then it goes to 0 on the other side very, very fast. Because it goes to 0 here as e to the minus x. When x goes to minus infinity, e to the minus x goes to infinity, and e to the minus x goes to 0. Okay, so it's very asymmetric. This is a very asymmetric distribution. And this distribution has a name, it's called Gumbel distribution. And we have already seen this Gumbel distribution when we discussed balls and boxes, if you remember. Okay. So what I want to do is to derive this limit by studying the case of a Gaussian. Okay. So let's say that p of x is equal to y over square root 2 pi e to the minus x squared over 2. So what we want to do is to compute this integral x squared over 2. Okay, we want to find an and bn such that this integral, as n goes to infinity, gives us a finite limit. Okay. Now, as we already saw several times, so this is when because an plus bnx will go to infinity as n goes to infinity, so this is x prime. Then I can use the asymptotic expansion of this integral when the lower limit of integration is very large, that we have discussed several times. So this is n over square root 2 pi, which is here, times e to the minus an plus bnx squared over 2 divided by an plus bnx. Okay? Very good. So now I want to make this finite, and let me expand this more in detail. So this is an squared over 2 minus an bn times x minus bn squared x squared over 2. Okay. Now I want to make this finite, and the main issue is to take care about this n. So if I want to take care about this n, then I need that this term should account for this. So an should also be large. Okay. So if an is going to be large, then bn should be small, because otherwise the dependence on x will not be independent of n. Okay. So essentially, the first thing is to make sure that n e to the minus an squared over 2 divided by an gives us a finite limit, okay? And in order to do this, so if I take an, which is equal to the square root 2 log n, plus another constant, let's call it Cn, where Cn is much less than square root of 2 log n. Then you see that a squared n over 2 e to the minus a squared n over 2 is exactly equal to 1 over n, and it cancels this one, okay? So, then here, what I can substitute here square root 2 log n plus the Cn square, which is 2 log n, so divided by 2 is log n plus the Cn times square root of 2 log n plus Cn squared. Now, if I, so this, as we said, will go away with this. Then this will be essentially subleading. So what I have is e to the Cn square root 2 log n with a minus sign, minus Cn squared over 2 minus an times bn, so square root 2 log n times bn x minus Cn bn x minus b squared and x squared over 2, okay? This is divided by square root 2 log n plus Cn plus bn times x, no? Which is this, okay? Now, the next problem that I have is that if I want to make this limit finite, then the Cn here should be so that it cancels this, this behavior. So assume that these two terms are small compared to this. So then I have to take this Cn such that this is finite, and what I have to do is take the Cn as minus 1 over the square root 2 log n. Sorry, and there is the factor 2 pi here, square root 2 pi, times the log of this, okay? The log of the square root of 4 pi times log n, okay? So if I take this, then asymptotically this and this will cancel, and also you see that the Cn, which is this, is actually goes to 0 as n goes to infinity, so that this goes to 0 And well, this is also very small compared to this. So if I want to make this term also finite, then I have to take Bn, which is equal to 1 over the square root of 2 log n. Okay? And if I make these two choices, then this integral here will just converge to e to the minus, this is 1, just e to the minus x, which is the c of x that we discussed for the Gamble distribution. Okay, so final thing that I want to discuss is the fact that this limit may not always exist, and I want to give you an example. So imagine that you take p of x, which is equal to 1 over x times log of x squared for x larger or equal to e, okay, and is 0 otherwise, okay. So you see, this is a probability distribution that goes to 0 extremely slowly, very, very slowly. It goes as 1 over x divided by logarithmic correction, which is barely normalizable. So you can check that the integral from e to infinity of the x of p of x, this is equal to 1. And now you can think, well, let's imagine that I have a sequence of IID rows from this, and let us ask, well, can I find coefficients an and bn such that asymptotically you can have the maximum of these n random variables can be written in this form? Well, the answer is no. And the reason why the answer is no is that you can introduce transform random variables which are the log of the xi, and this random variable will have a PDF which can be derived from this probability distribution while making a change of variable. And what you will find is that the probability distribution of this random variable is 1 over x squared for x larger than 1. So in this case, let me call this x tilde. So x tilde is log of x. So you see that this is 1 over x tilde squared, and this 1 over x is just the Jacobian of the transformation from x to x tilde. Okay, so now it is clear that now I can ask myself, what is the maximum of n IID random variables drawn from this distribution? And this is a clear answer, because it falls in the first case that we have discussed. In particular, this would be a case with gamma equal to 1 in the first case. So the b tilde n should be just of order n. and the distribution, the probability distribution h of x will be equal to e to the minus 1 over x. Okay? It's just the first case that we have discussed. But then, if this limit exists, we also have that Zn, the original variable, should be the exponential of the maximum. Because if the random variable, if the maximum of these random variables, of the log of this random variable is given by z tilde, then the maximum of this random variable is given by e to the exponent, e to the z tilde event, or e to the maximum of the x tilde random variables. And then you see that this is an asymptotic form, which is of the type e to the n times a random variable. And this asymptotic form is not of this form, cannot be put in that form there. Okay? But so this is a rather pathological example. Because, as I told you, I mean, this is a distribution which is really, really very broad. So, to summarize, what we have seen is that limit theorems for extreme satisfy the same type of properties of limit theorems for sums, in the sense that you can find coefficients in such a way that the distribution of the maximum is described by a random variable which has a universal distribution. And so the reason why this happens is essentially the same as the reason why it happens for sums. Because we have seen that you can perform the sum in steps by grouping variables in pairs, then in pairs of pairs, then in pairs of pairs. But you can also do this for the maximum. Okay, so the maximum of these n random variables can be written as the maximum of the maximum between the first two and the last two, and the maximum in pairs. And then you can go on in this way. So you can compute this maximum by first doing the maximum in pairs, then doing the maximum of pairs, etc., etc. And so in the end, what you want to so understanding what are the limit properties of maxima is essentially understanding when you compute the distribution of a random variable, which is the maximum of two random variables, and when you iterate this recursion gives you a recursion from the probability distribution of the random variable xi to the random variable of this one. And again, you can apply the same idea to this recursion, where essentially you do coarse graining and then a rescaling, and you can look at this renormalization group transformation and find a fixed point, and the fixed point will describe the universal distribution of the random variable for the maximum. So essentially the fact that there is a universal distribution relies on the fact that both the sum and the maximum satisfy this group property, so that which is essentially an associative property, so that you can perform both the sum and the maximum in steps where you block, where you when you group the variables in blocks and then perform the sum of the maximum in blocks and then perform the sum and the maximum of blocks and so on. Okay? So the fact that you have this group property implies these universality properties, and it also implies scaling. It implies that this coefficient Bn have a form which is scale invariant, which is typically a power law.